Okay, at least live stream should be running. And I'll maybe give you a minute, but then let's start. Any questions before we get started? Any organizational things to sort? All happy, all good? All happy growing bamboo? I have one announcement. You may have seen this on Canvas in the calendar. We'll do normal lectures this week, normal lectures next week, but then the week after that, I'm away for a week, and so we just pause the module. You can call it reading week if you want. Some unis do that for all modules. So you just take that time off. The thing is, we have 10 hours of actual teaching content for a 12-week term. We'll use one extra week at the end for recap. But there's still 1 week left that there's no material to fill it with. If you look at the module description, it always says 30 hours teaching. So we're doing our 3 hours per week. That's 10 hours. So I don't know where it came from. It's convenient in this case. So you just get some week off and spend that on whatever you want. I've also published a new class test. Same games as for the past ones. So the new class tests, I think I gave you some 2 weeks roughly again. So it's covering some string matching topic on KMP. You can do the practice version to see exactly what you're supposed to do, and do that as often as you feel like, and then do the real one when you feel confident. I think that's all in organizational matters. Of course, don't forget the continuous assessment, but I don't think you will forget. Unless you have questions, let's get cracking on. Okay, welcome back to efficient algorithms. We're finally leaving behind all the topics that are often covered in undergraduate computer science classes as well to some degree, and now start some exciting topics that go well beyond that. And the first such topic is this one, Unit 5, parallel algorithms. So we'll look at how you can, on a conceptual algorithmic level, take advantage of the fact that basically all computers we have, apart from the smaller embedded devices, have multiple threads of execution, multiple cores. And so you need to specifically program them to take advantage of that. That's what we'll look at. My goal for you is to know some fundamental strategies how you can parallelize problems. We'll keep it away from the actual code, and this is unfortunately one of the cases where I can blame it on the technical side. The software tools for parallel programming are not as convenient yet as they have become for standard programming, sequential programming. So some of the things we'll touch on here need a lot more engineering work to be fast in practice than the sequential methods, just because there's more technicalities involved, at least at this point. I want you to also be able to say when a problem is not possibly sped up by parallel algorithms. And we'll look at the formal machine models for that allows such statements. We'll analyze algorithms, and that will require a little rethinking of what we mean by time. And we'll look at some concrete methods where the parallel algorithms are interesting. We'll look at more, but these are the non-trivial parallel algorithms. We'll start with the models, and then we'll look basically at 2 problems, string matching in parallel and sorting. And for sorting, we'll need some intermediate steps that maybe are so exciting in isolation, but without them, it seems really tough to get other problems going. So these are, again, fundamental building blocks, and we'll put it all together in the last part. Before we set the stage for that, let me ask how much experience you have with parallel programming, because this tends to vary a lot. I think we have very few students from the big data program. They usually do a little more of OpenMP, MPI. You do a little bit of that. What course is that? Okay, yeah. So you will do a little bit of that. You will see how it contrasts to what we'll discuss, and maybe enjoy the less tedious parts. Okay, I've only had 25 votes for the join code, and more here, so I'll probably show the code again, I guess. Okay, so a few of you among the 7 have done this, but also a lot of people have never touched any parallel programming. Now, I mean, this is probably a large chunk of the people who haven't really programmed before starting this course, so it's kind of obvious. But I think the subset of people who've done programming and parallel programming is much smaller than the set of all programmers. It's something that people are usually not so familiar with. There are many different types of things that could be called programming in parallel. So it's is also in the details of what that exactly means. Let me switch back to the attendance code, and we'll move on. I probably should have also asked if you've seen parallel algorithms before. I guess the answer is no for most. At least it's very rare that this is taught in undergraduate classes. All right, why do we care at all? If you have a lot of money to solve a problem, you can buy lots of computers. Maybe unless there's global shortage of semiconductors. But let's leave that aside. This is when I wrote that, there was none. And things will get better. In principle, money can still buy you lots of computers. Maybe just not some of the chips. But that alone doesn't make a program faster. It can't buy you time. If you want to solve a certain problem really fast, you have to make it work on several computers at the same time. And that can be a challenge. Now let's jump right into a distinguish two notions, which both can be called parallel computation. But they're very different in the techniques, and that's why we have to focus on one of them. The one that we'll look at is a shared memory parallel computer. So you can imagine it's one big device which has shared memory. That's the distinctive feature. So all the processing parts can access the same memory. But there's several processors. So to avoid using any specific technical jargon, I'll just say processing elements, which is standard terminology in the algorithms literature on parallelism, where a processing element can be a single core, or it can be a hyper-thread core, or it could also be an entire machine as part of a supercomputer. So supercomputers somewhere are in between those two. It's sometimes a bit tough to make the clear cut. Okay, let me finish this first, though. Shared memory that everyone can access, but several individual pieces that can compute. Okay. There's also the main communication between these different pieces that compute happening through memory. So there's certain, they can make this up. We'll have to program them to do it. But they can say memory location 42 is a special memory location. I use this to send messages by writing some specific value there. The typical thing of this I think this is still basically the same numbers. So you can buy these machines, beefy big compute servers, a lot of cores, but not those thousands, maybe hundreds. But they can have really big memory. You can have main memory in the terabyte range. It's expensive, but you can build these machines. The big other parallel form of computation is distributed computing. Again, we have same concept, different processing elements that can compute, but they have private memory, and they send explicit messages to communicate. So there's some network connection on top of the individual machines, and so they can only communicate by sending messages across the network. Think of a cluster or a compute center of the old style, at least, where the machines are fairly separate. So this is a different scenario, and you can maybe imagine that here the bottleneck will be the messages. If the network usually is orders of magnitude slower than the rest, and so the real dominating factor is the messages, and that's a bit of a different world. It needs different trade-offs. Now, supercomputers, I think these days are somewhere in between, because they are distributed systems by the setup. They are composed of individual machines, but they're connected by so fast network that they can almost be treated like a shared memory machine in some regards. So sometimes the distinction is not so clean. For us, keep this in mind. A single big beefy machine with a couple dozen of processing elements and huge shared memory. That's the main thing I have in mind for this model. The way we will model this, remember, we want eternal truths. So we want statements of the kind, no algorithm can possibly do this better than so-and-so, to compare it to the algorithms you do have. And for these statements, you need a formal machine model that tells you what are programs like and how is performance measured. And for this unit, that's the PRAM, the parallel random access machine. You may remember the RAM model. I hope you do. The PRAM differs from that by having several processing elements. No surprise. Now, the rest might be a little awkward at first. So kind of bear with me and pay attention. So every of these processing elements has an ID. And we always assume 0 up to p-1 are the IDs. And they can use this in their program. I'll come back to that. They also have, it's still the word RAM model. So they operate in words of so and so many bits, W bits. And that's a parameter of the model. Remember, we used to think the word size is roughly like logarithmic in the input size. And now we have another parameter p, which the number of processors also can depend on n. So our machines grow with the problems. I've discussed this back then a bit more. Maybe it's no longer such a shock to you. It's not unusual that for the algorithm formulation, we just assume we have as many processing elements as we'll have inputs. This is not usually realistic, but it's also not usually a problem for designing the algorithm. And I'll show you why in a couple of slides. But the thinking for designing the algorithm should be, you have loads of processors. No shortage of processors. Each of these, this should really say the same. All of these processing elements run a standard RAM program, as we've done it all the time, at least under the hood. And this time, we assume they all run the same one. And they run this to a good degree synchronously. So one time step is the same for all the processing elements. They run in lockstep. They do a step at a time. They can do different things because they can use their ID as a variable in the code. So they can branch off in different directions depending on which processing element it is. Each PE has its own registers, but the large memory, the unbounded memory of the RAM model, is shared. So they all access the same one. I already said they run synchronously. And so that makes it easy for us to define time. We can just count time steps again. If you're worried about how realistic the model is, that's usually the part that needs extra work. This is not how current hardware realizes parallel processing. What almost all software stacks above that do is establish some sort of synchronization. And so you can essentially emulate this. The question is how costly it is. So this is the engineering part I alluded to. There's some constant factor overhead involved in synchronizing the different PEs. And the goal in practice will be not to do this too fine granular, not after every little step. And often you don't have to. But for designing the algorithms, it's very liberating to ignore that part and worry about it separately. It's two separate concerns. And the good parallel algorithms that work on the PRAM, unless they exploit this very, very much, also yield good algorithms in practice on the machines that we have. Now, there's one problem that if you think about this for a while, we say all the different processing elements run happily their program. A RAM program can involve reading and writing memory. So it could happen that two processing elements at the same time, remember, they run synchronously, lockstep. They could both try to write a value to one location in memory. And so we have a write conflict at this point. And we have to somehow resolve this. Now, as a theoretician, that is a question of the model. What should happen? And there's different models which restrict what the programmer is allowed to do. And they're all reasonable in their way. One model is the exclusive read, exclusive write PRAM. I know these acronyms are awful, but that's how it's stuck. So I think it's best to just remember what this stands for. So the exclusive read, exclusive write parallel random access machine model just restricts the programs so that it never happens that any two processing elements at any point in time read or write the same location. Very restrictive, but at no point will that ever happen that we get this conflict situation. If you think about it for reads, it's actually not so controversial. What should possibly go wrong if they both read the same location? They will read the same value. Not much harm done. So the crew PRAM allows concurrent reads, but enforces exclusive writes. That kind of still has no problem. Just the writes cannot go to the same location at the same time. And again, so you should think about these models as before they start running, they look at the program, and if the program contains writes at the same point, they somehow magically recognize that and say, nope, I'm not even starting. It's the programmer that has to prove this up front, that your algorithm satisfies the restrictions. So it's really a restriction on the programs, not necessarily the machine itself. The crew is often the model that we'll think of because that's what programmers often find easy to work with, because that is free of weird things. Unfortunately, that's not what current hardware does. But again, I said that one of the complications is getting performance right in this space is tough. And so there's usually hardware that does one thing, software above it that tries to restrict the most confusing things from happening. The other model is the concurrent read, concurrent write PRAM, which just allows everything. But now you have to somehow say what happens if two processing elements write to the same location. You can resolve this in a different way. A simple option, sounds awkward, but can be really powerful, is the common CRCW PRAM that only allows concurrent writes if they have the same value. then again, no conflict really. Another option is the arbitrary one. And unfortunately, so this this is where your computer does, almost. You're allowed to write to the same location, but the abstraction doesn't guarantee you what happens, really. Unless you put other mechanisms in place to synchronize the writes, to make sure that they're properly ordered logically, anything can happen. That's what we call a race condition, and that's what plagues parallel programmers day in, day out. And I think we still haven't found a really good solution for this that is at the same time easy to use and exploits the hardware to maximal performance. Maybe we'll never do this. Maybe it's never going to be possible. So this is closest to the hardware, but if you can design a parallel algorithm to live in this space, no concurrent writes, it'll be much easier and faster to implement on a real machine. That's why this is our default, but it makes sense to keep all in mind as possibilities. Last slide on the model, I think, is what is the cost of an execution? Because we have several processing elements now, this is maybe a little less obvious, but space is still clear. It's just the total memory that is used by any of the processing elements. Time, a natural way to define is just the total number of time steps till all of the processing elements have finished. The make span in other terminology. So this is the real wall clock time you have to wait if you start the computer and wait till all the processing elements are done. It's often also called not time, because that's a bit ambiguous, but depth or span. Pick the term you like best. Depth alludes to a visualization where you say what can run in parallel is next to each other, and what cannot be parallelized goes below, and so then the depth becomes the number of time steps. Now this is new. We'll have a third one, a third metric that will be almost as important as the other. That's work, and that's just the total instructions executed across all processing elements. You might wonder why you care about this. An easy one is that's probably proportional to the energy you're using, which is much more of a discussion these days, especially in cloud compute centers. But there's another reason that we'll come to why work cannot be ignored. What are we aiming for in theory, at least, is minimal time, as always. We like to be fast. But we can't ignore work. So the best possible we can hope for is what people call a work-efficient algorithm. So that's an algorithm that's essentially as good as the best sequential method in terms of work. So you take an algorithm that only works sequentially. That gives you a theta class of the running time. In the usual way, we usually think about the worst case and so on. You take that theta class, that's your goal for the work of your parallel algorithm. Then in a way, it's supposed to spend, at most a constant factor, more total effort, but somehow squeeze that in time so that it can just be run in parallel on several processing elements. Okay? Do the three things make sense? Space, time, and work, or space, span, and work? Now a little corner case for you to ponder. Whenever we define a notion, it's useful to think about whether we're talking about the empty set, and nothing can possibly ever be work efficient. I'll wait till 40 people have voted. That's what we eventually had on the attendance code. Unless we're stuck at 35 forever. Ah. All right, so there we go. Yeah, it sounds like you should expect always to have this, but no, you can always have a work-efficient algorithm. Now the trick is it doesn't say that this has to be a fast parallel algorithm in terms of time. It just says work efficient. So you just take the best sequential algorithm that is work efficient. It's probably a crappy parallel algorithm unless you spend some time on it. By the way, like you don't need to change your vote now to reflect that you've known it up front and it's all. I won't look at these results. Also, the video shows that you changed your mind, which is always fun to watch. So one more reason for the recordings, right? All right. So the simple reason is you can take the sequential one, but again, the real interesting question is one that also improves the parallel time, and there it's not so clear. I want to finish this introduction on the model with an important argument that I think is often like is sometimes lost in the discussion, and it's very unfortunate. People often complain about the PRAM model that it's unrealistic because it assumes you have this humongous number of processing elements. And I think that point is missing the point. The other part, that it assumes the synchronous time steps, I take that criticism. That makes sense, and you have to worry about how to realize for some of the algorithms on the more relaxed hardware that we have. The number of processors is not really a problem. And the reason is Brent's theorem, which says whenever you have some parallel algorithm with span t and work w, or time t, work w, I'll use span to avoid the confusion with time. I can already remember some of the slides down. So I sometimes use span to avoid the confusion with time. You can also call it parallel time. That's is all the time we define, the number of time steps till everyone's finished. So you have an algorithm with time t, work w. Then you can always simulate that algorithm on a specific PRAM that has p processing elements in time that's not t, but t plus w divided p, and roughly the same work. So in a way, before we look into why that's true, I want to point out this this corollary of this. Didn't want to cross it out. If you have a theoretical algorithm on the PRAM that assumes whatever number of processors, it is actually a family of algorithms that could be tailored to any number of PEs. And if you know the work and span of this theoretical algorithm with as many processing elements as you want, you can always translate it to real time and work bounds for a specific number of processing elements. And so you can predict fairly well roughly how well it will do. And so it's much more useful than it first sounds. Now the argument, you will be disappointed by the proof of this theorem because it's very simple and also shows that there's a constant factor overhead paid in terms of the time that may not be negligible. Let's suppose we have a PRAM algorithm that uses many processors. And let's suppose many means 5, so I finish the drawing at some point. And so I'll draw the time downwards. This is time. We have time step 1, 2, 3, 4, and so on. And then let me draw the instruction that each processing element does. So it could be that we have 5 processing elements working on this, and they each do some instruction in time step 1. Then they do some other instruction in time step 2. And another in time step 3. Maybe this time not everyone participates because some are already done. And maybe there's just one, but then say in time step 5, they all come together and finish off whatever they've done. So how can it come to these gaps? They all execute the same program, but they remember they can use their processing element ID. So they might be idling around during some steps and wait for the others. So we'll see examples that's possible. Now let's suppose we have to simulate this. On a PRAM with only 3 processing elements. So how would you do it? Well, yeah, you only have the 3 processing elements. So okay, start at 0. So all you can really do is pick one of these tasks at a time. So you take the first 3, put them here. And then there's 2 left. So you need another time step where the same processing elements now do the remaining 2. So what you do is just round robin schedule the tasks that you need to do. And you may need a little more time to do this if all the processing elements participated. But sometimes you can do it in the same time. Sometimes you need an extra step. How bad is this algorithm in terms of time? First of all, the work is almost the same. You need a little overhead for the scheduling, who does what. I'm only sketching this very high level. So work will be similar, just a little overhead per step. Now, if you look at each of these, okay, I need to turn this off. How long is this? Well, it's the number of processors. We don't have let's call this P prime. That's the or big P for, because that's larger. And now we divide it by the little p. That's how many rounds I need, and I have to round up. Now I do this for every time step. And if I sum this up, I have at most capital P in each step. But actually, if you sum it up, you can only have as much as you have work on the right. So the total number of boxes is the work. So if you sum up this term over all the faces we've done on the left, this capital P will sum to work. In a way, it's how many are active at each point in time. So it's, I should have introduced proper notation for this, but if you say capital PI is the number of processing elements that are active in step I, then PI divided P rounded up is the number of rounds you have to do in this round robin schedule. And if you sum these up over all the times, then the PI is summed to W, but because of the rounding up, you need to add a plus T. You have at most +1 in each step. Let me smuggle in an intermediate step here to make that clearer. If you round something up, you can always bound that by adding 1 and drop the rounding. And then that sums to W over P plus T. Okay? So at least in theory, you can always simulate whatever parallel algorithm you have on the number of processing elements your machine has, and you still get a reasonable estimate for the time. Now, if this time is good or not depends, right? It depends on T and it depends on W. Any questions on the model? Okay, it seems there's some technical issues on the live stream. But other than checking my connection, there's probably nothing I can do about it. I'll put the question live. Maybe people in the live stream can answer it on there. All right. Questions here or remote? If that's not the case, then let's have a look at the first algorithmic problem. Fighting with the computer. Stop it. Imagine there's some music coming for the technical break. You can already start thinking about how you would parallelize string matching. Maybe you have an idea up front that's good. Okay, everything's still running and ready for the next part, I hope. In the next subsection, I want to look at the string matching problem again. We've just covered a lot of algorithms for string matching in the last section, but they were all sequential. We didn't care about parallelism. It turns out this is a nice problem to get started. And the reason for that is that some problems are really easy to parallelize. And we call those embarrassingly parallel. It's a kind of a cute term, but is one of those vague things again. There's a way to split the algorithmic problem into small subtasks. And each of these subtasks must be computable, solvable, independent of all the others. If a problem is like that, you can just assign all the subtasks in parallel to different processing elements, and then you get a huge speed up from the parallelism. A typical example that's clearly like that is if you have two large matrices and you want to compute the sum. I'm not talking about matrix products for now. If you just do the sum, remember sum of matrices is just the element-wise sum. So every element, every entry in the output of this algorithm is depending on two things in the input, and it's not talking to any of the other subproblems. In a way, matrix multiplication is similar. You can also compute those in an independent way, but the smarter algorithms for matrix multiplication don't do that. They try to reuse some information. Whereas for the sum, there's nothing to be gained. It's easy enough as it is. Such an embarrassingly parallel algorithm embarrassingly parallel problem is the best case for parallel algorithms, then there's not much that you need to think about. Unfortunately, most problems aren't like that. And I think it's insightful to think about sorting. Again, we've talked about that at length in the unit before the last one. We didn't care about parallelism at the time. But if you think about this task of rearranging elements in a list into sorted order, it's not so clear what an individual subtask would even be. We had divide and conquer algorithms, so they started with breaking things in half, and then that was subtasks. But it's really not so clear how you can define small subproblems that are also independent of each other. We'll see that some parts are like this, but you need to work your way around them. It's not obvious. So sorting is not necessarily one example of such a problem. How about string matching? Without telling you anything about the problem and how you potentially could solve this, I will just ask the question now, and we'll come back to that later. I don't want to show the answer yet, but okay, well, I'll wait till we have 40 or so, and then I'll just lock the question this time for the pedagogical effect of looking at it later. So if you want to cast your vote, do it in 5, 4, 3, 2, 1. And because the live stream is 5 seconds delayed, as if it means, so let me talk and waffle around for a while. 3, 2, 1, locked. All right. We'll come back to it. So it's an interesting case. We've seen a lot of algorithms. In a way, all the algorithms for string matching that were particularly good according to the metric of Unit 4 were exactly the ones that exploited maximally the knowledge from the previous step. Remember, we had character comparisons was what we counted, and we tried to not do redundant comparisons. But by the essence of a non-redundant comparison is one that we haven't seen, and redundant was we build on the knowledge we have. So it's kind of the opposite of this inherently or embarrassingly parallel. It sounds like this is exactly not what you want to do. So we might need different algorithms. Before we dive into the problem a bit more, I want to rephrase it that makes it a little more natural and simple for parallel algorithms. It won't at the end affect the vote that we've had, but this makes it a little cleaner. Unit 4, we said string matching is find the first occurrence of the pattern in the text if there's one. Now I'll say just report all. And the reason is then we don't have to communicate between the processing elements to find out if we should answer no. If any of those solves a subproblem and doesn't find an occurrence of the pattern, it would have to ask all the others, hey, did you also not find a pattern? And only if everyone says no, 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 then you can report no match. To avoid us that hassle, to spare us from that hassle, I'll just say everyone reports a match if they find one. And if not, the user will have to figure it out later. That's a bit more natural in the parallel setting. And then it's natural to define subproblems as checking individual guesses. So we have some way of defining subproblems that comes from string matching. And we could say that checking of one guess is a subtask. So let's try the easy thing. Let's go back to the brute force algorithm for string matching. I've copied this on the slide. It's almost literally the same as what we had in the last unit. What I added, obviously, is the red part. I'll comment on this type of parallel pseudocode in a second. One thing that I took out was the sequential brute force method at the end had, if none of the iterations returned a match, then there was this return no match. We don't do that here. So the type of code we write for these parallel algorithms will usually be a for loop or something similar like this. And we just tack on this keyword in parallel, which is supposed to mean all these iterations of the for loop, this inner part, that's repeated many times. Sequentially, we just go through all the different values of I. But now if I write in parallel, the understanding is we can do all of these, each on a different processing element. And the index, the loop variable, gives us the index of the processing element. This inherently requires that all the iterations of the loop body can be done independently. If they cannot, if they build on each other's computation and you don't pay attention, that's your problem. This is similar to if you have programmed in OpenMP, you may recognize that this is precisely one of the things that OpenMP can do for you. And there's all sorts of caveats. If you use this without too much thinking, then things can go wrong. That's in a way the same with this pseudocode. The inner loop hasn't changed. So each individual processing element is getting some index I, a guess, and then it just goes through the pattern and checks if it matches all along. And instead of returning, I just say report a match at I. That's some vague intermediate stage. What we would really need is another thing, another step afterwards that collects the results. This is a problem we'll talk about later, so I'll leave that out. Long discussion for a simple algorithm, but I wanted to make sure that the parallel pseudocode is clear. So if you have questions on how the code is supposed to work, or what is supposed to mean to write a loop like that with in parallel, then let me know or ask. The other question is, how good is it? And remember, we'll have two measurements of time, span and work, or time and work. That's one of those slides where I wrote time, but it's parallel time or span all the way through. What's the time for executing this algorithm? Usually when you see a for loop, you think, oh, this is so and so many iterations, but haha, it's in parallel, so it doesn't count. Each of these steps is done in parallel, so we only really look at what does the longest of these iterations, how long does the longest running iteration take? And that's a loop over the pattern, so it takes time linear in the size of the pattern, theta of m. Now this is if you use the code as given. You'll see in the tutorials that for this task of checking whether two strings are equal, you can actually do better depending on the machine model. If you allow some concurrent accesses, you can do this much faster, which is an interesting speed up at that point. Unfortunately, it's all not really that useful because work is really poor. If you sum up the work that you do, it's in the worst case, you do m comparisons in each loop iteration, and you do this across roughly n processing elements. So this is, in a way, like the brute force method used for sequential algorithms, for the sequential brute force algorithm. And we've discussed at length in the last section that there's much better solutions than, for the worst case, than the brute force algorithm. So work is not good. Time is great. You can't possibly beat constant time. But if you remember Brent's theorem from a few slides back, unless you have absurd numbers of processing elements, that won't help you. If work is bad, the overall time is still slow. Maybe we can do something else. And of course, we'd like to take advantage of all this fast sequential string matching that we've developed. And it turns out a fairly general technique works here as well. You can use blocking. You can break the problem in a different way into subproblems. And that allows you to improve the work. So what we'll do is we split the text into overlapping blocks so that we never miss a character. So let me illustrate this on a quick example, just graphically. So then I think it's clear why we do that in exactly this way. It doesn't need a power of 2. So that's your text T. And I don't care about the actual letters here. It's just conceptual picture. And let's say M is 3. So the pattern could occur here, or it could occur here, or it could occur here at any of the positions, right? It's wherever you have a 3-character long stretch, that could be one occurrence of the pattern. What we want to do is to use a fast sequential algorithm for a small section of the text and check if the pattern is in there. And the trick here is that works basically out of the box, but you have to make the portions of the text slightly overlapping. So that the length of the overlapping parts is 2m minus 1. This is 5. And so the first 5 are assigned to one processing element. So all of these red ones will be caught by the first processing elements. If there's an occurrence, it will find it. Now, how about an occurrence that spans this boundary? That might not be caught. That should go one further. We have to catch the orange ones as well. So we overlay a second one, starts at M, and also goes 5 long. And this will cover all the orange ones. And then for the next red one, which again would escape this one by 1 character, you have another start. So you start at 0, at 3, and then at 6 again. And so that red one would be caught by that one. OK, so it's a simple picture proof that no matter what you do, one of the blocks will always see an occurrence of the pattern if there is one. With that preparation, the algorithm is really simple. You just iterate over all the block IDs if you want, and compute what is the portion of the text you have to look at. That's these 5 characters in our example. And you can use, say, the KMP algorithm to check if the pattern occurs in there. Now, this just to save effort, I stored the result. If KMP finds no match, then you don't report anything. But if it does, then you report the result. So probably clear. Is it clear to you guys that the algorithm works correctly? There's basically two things. It should never report a match that's not really in the text. That won't happen because it's looking at a substring of the text, and it only says, yeah, there's a match if I found the pattern there. The other thing is it cannot miss a match. That's what I tried to prove with this picture. No matter where the match starts, one of the blocks will entirely contain that these M positions, and so we'll have to find the match. Again, second question, how good is this algorithm? If we look at the time, again, parallel time means this parallel loop doesn't count. It's happening all at the same time. So we just have to find out how long the loop body takes. We call the KMP algorithm, which we know has running time n plus m for a text of length n and a pattern of length m. Now we're not using it on the full text, but on a small snippet. So if you insert that, you get overall linear time in terms of the pattern, so a theta of m, because we use it on a very small piece of the text. And if you compute the work, is also work efficient. The reason is that we have not so many blocks. So even though each block uses theta m effort, we only have n over m roughly, plus 1 maybe. That's still theta of n overall effort, overall work. At least if you assume that the pattern is shorter than the text, that's work efficient. And maybe a simple check can catch that corner case. So that's great. We have a work efficient algorithm now. But we've already seen on the last slide that the parallel time m is not the best possible. We've had a better algorithm just where the work was crap. So if we come back to this question, the correct answer is the third one, which a few of you got. Okay, interesting rendering of this character. It's embarrassingly parallel in the sense that you can solve it as efficiently as possible, so that the total time is dominated by the work efficient part. If the length is much longer than m, then you can say that this parallel time theta of m is not bothering me too much. The overall work divided by the number of processing elements that I have is probably dominating this. And so there I would say it's embarrassingly parallel. Turn the argument around and it's clear that it cannot be yes. If the pattern and the text have roughly the same length, what you would get in this case here is parallel time stays the same and work stays the same. So you don't speed up at all over the sequential algorithm. And so that's work efficient, but not really parallel. You haven't sped up anything. So in a way, it's easy to parallelize string matching only for short patterns. That is all I want to say about the simple string matching methods that we'll look at in detail. The two things I showed you, the code is really simple. It's also reasonably efficient to implement. You could even distribute the text and it would still work. But when the pattern is also long, it might not be so helpful. So you could ask, could you improve on this? Can we get work efficient methods where the span is also better than m? So we can really parallelize somehow non-trivial this matching part. This is only possible if we can parallelize the matching process. That we can do if it's just checking two strings for equality, but the pre-processing of the pattern is also part of this. And as far as I know, this is not possible with easy methods. But people have figured out more complicated ways to do that. I skipped those here. If you're interested to see a part of this more complicated algorithm, you can check out the recordings from last year. But I took it out in favor of some other things, also because it was not the entire story. There was always the pre-processing missing, which is much more complicated. So it was never so satisfying for me to teach that, showing you this nice, lovely bit that I could explain and then leaving off with this black box that we didn't dig into. Now the black box is just a bit bigger. But I want to mention, at least in theory, you could solve the problem faster. You can do log m times. That's, again, an exponential improvement if you want. Even if the pattern's long. If you have this concurrent write, you can even do the matching part much faster. For the pre-processing part, there seems to be barrier, a lower bound that you cannot do it in constant time, even if the machine allows you concurrent writes. And again, no details on that. Just so that you don't walk away and say, oh, all the simple methods don't work, so nothing works. That's not quite true. In terms of the practicality, I'm not sure if these methods ever have been implemented. So that's maybe the statement to make. Questions on string matching and parallelized string matching? I think it's a good point to do a little break so you can think about questions. Let's do just a quick 5-minute one. All right, ready to continue? I'll have to leave you a little early today because we have our staff meeting right after this. So it'll come at a big disappointment that we won't finish the unit today, I think. I know you're shattered. All right, everyone. In the next subsection, I want to show you some primitives that will be part of bigger parallel algorithms, in particular for parallel sorting. But we should also show that you have to learn some new building blocks for these kinds of parallel algorithms. We'll see that most problems are not embarrassingly parallel, but they contain some parts that are almost embarrassingly parallel. So many problems have this double nature. There's parts that are easy to parallelize, but then there's other bits where they seem to build on previous results all the time, and so you need tricks to get these steps done efficiently and still make use of the parallelizable part. I know that's so vague that it's close to useless. Maybe it'll make sense after you've seen the examples. It turns out that luckily, in a way, there are some building blocks that are useful many times, and we'll study some of those. The first of these building blocks is called the prefix sum problem. And it's formulated in an abstract way so that it is useful and applicable to different scenarios. It may look a little unmotivated at this point, but bear with me, you'll see on Monday what it's good for. The input is an array of numbers, as so many times in this module. The goal is to modify this array, so you're allowed to do this in place, to modify the array so that afterwards it contains the prefix sums, which means at position I, you're supposed to have the sum of the first of the elements up to and including position I, which are I+1 numbers, I guess. So here's an example. Here's the input. Here's the output. Note that so we always have that the first two entries are the same. If there's zeros, that means some things stay constant in the other array. And an entry up to here, so it just sums up all the numbers up there, and that matches. It sums up to 15. I guess the definition of the problem is easy enough. Now again, bear with me for why this is a useful problem. Without telling you much, let's have a vote on what you think is possible for this. And now first, just sequential, right? So you, I'll maybe show the problem again. You're supposed to do this just sequentially, standard algorithm, coded in Python, whatever you want. How fast can you do it? In a way, there's no wrong answer to this question. Well, maybe there are some wrong answers if it's impossible. But if you vote something, if you vote the highest number n cubed, it's never wrong, right? Because you can do it in that as an upper bound. But maybe that's not the most interesting algorithm then. What did I say? Wait till 40? $34. Do we get some more? $35. I should have split this up and now first show you the code and then have you vote again. In the interest of time, let's not do this though. The answers are very mixed. A few went for the safe option of n cubed. I guarantee you it's doable in n cubed time. A big O of n cubed is a safe bet anyways. Yeah, if you can do it in log n time, please find me for the thesis later. Sequential time, right? No, sorry, I'm not supposed to mock you much for this. So linear time is what we can do. Sequentially, I think this is inevitable because you need to read the array to produce the result. If you think about just the last entry, how are you supposed to do the sum of the entire array? Well, the last entry is the sum of all the numbers. How are you supposed to get that sum without inspecting every position in the array? I think this is not possible in the worst case. How can you do it in linear time, though? Here's the code. It's very nice and slick and simple. Oh, you don't see it. I forgot to switch back. There we go. So I was waving around on this slide. The last entry in the array is the sum of all numbers, and you need linear time to find that. And here's the code. For the dramatic effect, it's just 2 lines, really. The trick is you compute the sums from left to right, and then you use that. The next sum is always the previous sum plus 1 more element. That's how you can compute all those sums. Even though if you wanted to do those, we'll come to that if you do it in parallel. If you wanted to jump right in the middle and compute one of the sums taken out in isolation, you always need linear time in distance to the beginning. But if you do it sequentially, you can build on the previous result. That's great. It's actually very, very cheap. You do the number of additions that would be needed for just computing the last entry in the array, the total sum. But along the way, you get for free all the other partial sums. It's just convenient that you can leave them in the array. Now, the big problem for parallelizing this, of course, is that's maximal data dependency. Every operation, every iteration of this loop uses what was just computed in the iteration before. So that's not going to work for parallel, not if you want to get the parallel time down. And to focus our mind, let's reduce the problem even further for a moment to just computing the sum of the array, right? So this algorithm does this in one particular order, and that's depicted in this tree. You have n inputs, n numbers that you want to sum up. And what we have is a binary addition operation that can take 2 numbers and compute its sum. So you inevitably have to do n-1 additions because it's a binary tree. There's no way to get by with fewer internal nodes. But what you can do is look at a different binary tree. That's the binary tree that belongs to this code. You always compute it, the previous sum, and then add 1 more element to it. You don't have to do this tree. You can do a balanced tree instead. And now, if you compute this bottom up, you notice that a lot of things, the way the tree is already drawn shows this. A lot of things can be done in parallel without data dependencies. I can add these 2, and I can add these 2. They don't interfere each other. So I can do level by level bottom up. This is the first time step. That's the second time step. And then there's one last time step. You see it gets less and less busy. So here 4 PEs were busy, here just 2, and then just 1. But we reduced the height of the tree. Here the height was, 7? And here it's just 3. OK? Cool. So we want to do that. And the only bit that's left is to do this not just for the sum of all numbers, but all the prefix sums as well. And it turns out that you can do this with a simple trick. You basically simulate this algorithm for all the prefixes all at the same time. And you can reuse some of the partial examples. So I'll show you how this works on an example, and then we'll have some code after that. Here's your input. In round 1, you take adjacent pairs and add them up. So this new cell is filled with these two and their sum. And you do this for all the entries. Note that the sums are overlapping and all that. We'll come to it. I want to point out that after this first round already, the first entry is final. Well, it was ready right from the beginning. And the second entry is final. It contains its prefix sum, but all the others aren't. In the next round, we'll do something similar, but this time we take the element that's above us and 2 steps back. And maybe you can just, by pattern matching, guess how this might continue. You double the distance you jump back in each step. So here we went back 1 cell, -1, I guess. Here we went back 2 cells, 4 cells, hard to draw, and 8 cells. Whatever the gray arrows are right, and whatever I'm drawing may or may not be. If you pick out any specific element, you can see the binary tree that we've had for just the sum embedded in this. There's maybe a bit thicker. So we have these two. And the trick is that the final sum consists of 2 subtrees, each of which consists of further 2 subtrees. And what we'll have to see is that eventually everything's covered. Sorry, I'm just blindly continuing here. It's not what I wanted. This one and this one. And these two. Now I will color in all the top row, won't I? Apart from the last one. Let's make that a bit more economically. Okay, I'm totally messing up the picture. But maybe you can see the binary tree a little nicer now, and I forgot one. No, sorry. That's the only one that shouldn't be in there. Yeah, that's subtle. It's not a complete binary tree. That's why I picked the second to last. There's one dangling leaf left here. What you can see just visually is that all the elements are in there. And it's the same binary tree that we've seen before. All right, but doing it this way, you get all the binary trees at the same time. Writing this in code is not too hard. It's just a little messy because you have to keep track of the indices. But that's what it looks like. We'll do the rounds. These are round 1 and so on. That's the height of the tree. The rounds go from 1 up to log n rounded up. Step is how much do I jump back for my single addition? That's powers of 2, as hopefully you've noticed that pattern here as a computer scientist. So that's the step size. And then the parallel part is just this inner loop. In each round, we do for each of the positions in the array. So in round 2, for each of the positions that are not final, that's why this starts not at 0, you compute first the new sum, the value that's above you and the one a little further to the left. You compute that sum and then you store it. Now, I might have written these 2 lines in one line, right? It's doing the same thing. Now, I split it up in this case to point out a subtlety here, which the PRAM model is essentially fine doing it that way, but you have to be careful if you implement this on real software or programming languages with parallel support. We have to make sure that all these reads in that line from all the processing elements are done before any of the processing elements start writing back their results. Because otherwise you would read the new value and they would get out of sync. You have to make sure that all the reads in round I are done before all the writes in round I, and then you can continue with the next round. Is it clear why? Otherwise, you might end up having some numbers summed more than once because one processing element ran ahead and already did a bunch of additions. Now you grab this and pretend it's the old value, but then you add things several times. So that's one of the things that are easy to write as a PRAM algorithm, but need explicit synchronization if you do this in most implementations. Synchronization is implicit for us, which makes the code clean. But I wanted to point this out here. Okay, we still have to analyze how fast that is. Remember, we had sequential time, linear. That's the goal for the work. Now, I know the answers are here, but let's go slowly over this. And I have two colors because we want both work and time. So let's first be in time mode, so the green one. We run the overall, the outer loop is not parallelized, so we have to do this sequentially. So we have log n times this inner loop. Now, this is one step, but that's constant. But then we have a for loop that's parallelized. So for the time, we can ignore this. We just look at how long each body takes. And that's, again, constant time. It's just two operations each, or a bunch of reads, an addition, and a write. So what does that mean for the overall loop? It's log n times constant. So we have log n overall. That's the time. Okay? It will turn out that this is basically best possible for this problem, at least for some of the parallel models. If we look at work, the only difference, so this is the same, this is the same. The difference is that this loop now is done for all the different pre-E's. We sum that up. So we have to sum up this, and I'll be generous and say this is order n. Some iterations later are cheaper, but let's just do a generous upper bound, which turns out to be a sharp theta bound. So you have linear in each iteration, and overall n log n. Okay. You could write this here more specifically by subtracting the step and then write it as a sum, and you'll come to the same overall theta conclusion. So we have n log n work, but a sequential algorithm that we've seen before was linear. So it's not quite work efficient yet. It's a bit worse. But hey, it's not that bad either, right? It's a log factor overhead. So unless you have really few processing elements, maybe that algorithm is still a substantial improvement, because the sequential time is really fast. It goes from linear to log. The best possible here comes in a way from just looking at the sum. If you look at the simpler problem of just summing up n numbers, as long as all you can do is take two numbers and add them up, you have to spend you have to spend a linear number of additions, And you can work out that it's not possible to interleave them better. The binary tree has to have log n height. In a way, this is not atypical. We often have a certain trade-off. We can get a bit more parallelism, but then blow up the work. We've seen that as an extreme case for our first string matching algorithms. Now, sometimes, though, you can actually get the best of both worlds by just thinking a little harder. In this case, there's two ways how you can make our parallel prefix sums work efficient and keep the parallel time. You can do it with doubling the parallel time, which is a little more involved, so I'm not doing that. I'll show you something that effectively triples the parallel time, but brings the work down. So in theta world, where we ignore the constant factors, we keep the time but bring the work down to linear. Let's see how that works. And that's, again, before we dive into the details, I know it's a wall of text. I should have split that up. The key thing is that this is a template that works more generally. If you have an algorithm that's good in terms of parallel time, but not work efficient, try to find a way to break the problem into blocks where you can use an efficient sequential algorithm on small pieces, and then on the aggregate results, use your work inefficient parallel algorithm. If you can reduce the size of the problem enough so that this work inefficiency doesn't carry through, and the blocks are small enough for the sequential algorithm to still be fast, you can improve overall. Again, as always, I'm not sure if it's useful to first give the general template and then the example, or the other way around. You usually understand things the other way around, but I think warning you up front about what's to come is helpful. You'll be my judge. Here's how we do it in this case. We choose a block size of roughly log n. So this will just be sub-segments of the array of log n elements. We break the conceptually break the element into blocks. No sawing needed. And then in parallel, we compute the prefix sums on just the little pieces. For that, we use the sequential algorithm, and then we'll use the sums of these in the work inefficient parallel prefix sum. And let me show you an example for that. At least like not a fully worked one, but a conceptual one. I think that makes it a bit clearer. So we start with 12 elements in our array. And suppose the block size is 4, which it is if you take the log of 12. I didn't just make that up. Good. So we'll have 3 blocks, right? If there are 4 elements each. I'm just trying to draw the array with cells. We don't really care about the numbers in there. That's why I said it's not a concrete work example. We're just summing numbers up. You can sum numbers. We don't need to do that in detail. So this is index 0, then 4, and then 8. Right, so let's look at the different steps. The first one is this local computation, where we keep local to the blocks. So we have conceptually broken the array into 3 pieces containing the same numbers. And you know what? Let's make it a concrete example, but a boring, trivial one. Let's just say it's filled with 1s. It's easy to keep track of the sum then. but it's a little less opaque. The local prefix sums, they just compute the prefix sums in this block using the sequential algorithm. So I will fill this all with 1, 2, 3, 4. Okay. Then the next step says take the last element of each block, namely these guys, the rightmost element, and compute the prefix sums for those using the new algorithm, the one with the fancy binary trees embedded. So we take this one, and this one, and well, I guess pretend there's a huge array with just the force in there, and compute the prefix sums of these. So that will give us, that's before, and then after you get this. Okay, that used up much of the slide's space. We'll see. And then we come back to the blocks. And add the global prefix before that block to all the values within the block. So what that's supposed to mean is we copy our orange part. Okay, I went too far with this one. Let's make that a bit smaller. This step says to all elements in here, add the 4. To all elements in this block, add the 8. I can do this in parallel over the blocks. So what I'll get is these stay the same. Then these get to 5, 6, 7, 8, and these get to 9, 10, 11, and 12. That's a 12. Okay, which is the correct prefix sum. Obvious to check in this case because we started with all ones. If you sum up as many ones as you have, then it should be the just the numbers 1 through 12. That was the last step. So that correctly computes the prefix sums. At least it worked in this example. Now let's see what the time and span for this and work for this is. So let me put time here and work there. Then I can keep using my colors for the different phases. How much time do I need inside each block with a sequential algorithm? Well, how long is a block? It's b long. So for the orange part, I need theta b time, which is log n. Then I have the blue part, which uses the fast parallel prefix sum algorithm that we've just discussed, and its time was log n. But I'm using it on n prime, which is not n, but n divided the block size. Rounded up, so in terms of theta, it's n divided b. And that, again, is n divided log n. So we can say this is still, should I do the computation? If you take, sorry, this is a log n prime. I didn't write this. That's the size of the input, but the time for the blue part is log n prime. If you insert this definition of n prime into log n prime, then you get log n minus log n. That's the same as theta log n. And finally, the green part that's a bunch of additions. Again, each processing element deals with one block, so it's only linear in the size of the block again. So the overall time, if you sum this up, is something like 3 times the previous time. And, well, I don't have to copy this, so this is summarized here again. I think the explanation is better explained step by step. So the time is, in terms of theta, still the same, log n, as we had it before. Let's look at the work, because the work was where we weren't happy previously. So work for the orange part, we're using the efficient sequential algorithm, and it's effectively the same as the span in this time. Every little piece just executes on its block. So that's log n. In terms of the work, sorry, that's per block. And we have n over b blocks. So that's linear work overall. For the orange part, the local sums. For the blue part, we're using the work inefficient algorithm from before. So the work there was n prime times log n prime. If we insert what our n prime is, we see that this nicely cancels. So it's n divided log n times log n prime, which we've already seen is log n, minus this small term. So that cancels and becomes also theta of n. So we've reduced the work by making the problem a little smaller. We reduced it by a log factor. And that was enough to bring the work to linear. And then the green part is, as before, we use n over b blocks, and each block costs us b, so that's linear again. So the overall work is linear for all steps. And that's work efficient because we know that's the best sequential algorithm. Okay? So that's probably the most involved algorithm we'll discuss in this section. It's more involved because it builds on other things, right? It uses previous algorithms as a black box. The nice thing about this, though, is you get an overall much faster algorithm without thinking too hard. You're just putting pieces together in a clever way. And that's much of the beauty in algorithms and data structures. Almost all the time, you do just this. You take pieces and put them together in a more clever, slightly more creative way. And that gives you a better result at the end. The magic or the skill is to know good pieces to put together and to see how they fit, which is sometimes incredibly hard. Even with a lot of practice, you sometimes don't see it as someone else does. But practice does help a bit. I have one last ingredient for this building block section, and that's this problem, which again sounds maybe a bit esoteric at first, but this will literally be used in the sorting part then. Suppose we have an array of numbers. We'll always have arrays of numbers, but we have a second array that tells us some of the elements are not interesting. I'm only interested in the elements that have a 1. And the ones with a 0, I'd like to not have there. So I'd like to copy out only the elements that have a 1 above them. We call that compacting a subsequence from an array. So you have a subsequence is a selection of the indices, so it's not a contiguous part, but could be spread out as you want. But subsequence means we want to keep the order as they appear in the original array. Now again, doing this sequentially is very easy, right? You go left to right, you keep a pointer to the next cell that's free. If you see zeros, you skip it. If you see a 1, you copy it out and move one cell further. Easy peasy sequentially. How do you do this in parallel? It's not so clear at first because it seems that, say, this 4, where this goes in the output seems to depend on what happened before in the sequential algorithm. But if you think about it for a moment, this is really just reusing what we've just done. You can use prefix sums on this bit vector b to figure out where the elements should go. Precisely for this 4, say, if we check where it comes from, the position in the array is essentially the number of 1s in b to the left of that point. So we would like to sum up the number of 1s here. If we sum that up, that's 5. And 4 is the 5th element. So apart from the plus minus 1, because we start indices with 0, that's the answer. So you can put this into code by this little algorithm. You have this b given as an array. We copy that out because we need b and we need to mess with it. So we copy it into C and compute the parallel prefix sums there. We're using one of the lovely algorithms you've just learned. And then we can do the following in parallel. If our processing element has one of those positions assigned that has a 1, then it gets active, otherwise it sleeps. And what does it do? It copies its element, a of j, into wherever c of j says it should go, -1 for the off by 1, we start indices at 0. Okay? So the trick here is this we know how to do properly in parallel. And we can use that to pre-compute where the elements should go. And then we do the actual data movement in a second step, in a second phase. That way we have decoupled the computation, like the sequential algorithm would go through this step by step and have this data dependency. The place where the element goes depends on the past. We have decoupled this by first computing where everyone goes and then moving them there in just one step parallel across all the processing elements. So let's see if you digested that part. How fast can we do this compacting? It's also interesting that it doesn't depend on how many elements you copy out. It's kind of irrelevant for the time and work in this case. I'm a little pressed for time, so I'm probably have to cut it here and reveal the answers, even though maybe you didn't have a chance to vote. But most of you got this right, so maybe this is easy enough. The answer is log and time and linear work. And the reason for that is look at this algorithm and analyze it. It basically does the prefix sum and not much else around it. What comes afterwards in terms of time is a constant step. And linear work, because we spread it across all the PEs. But both is dominated by the computation of the parallel prefix sums.